Welcome to essentially the first video in this channel. It talks about how unawareness of the underlying processes may lead to serious problems. To make the elaboration more concrete, I will use a story about caches and memory leaks. In the old days of computing, there was an intimate relationship between a software engineer and the computer, in a sense that the software engineer knew exactly how the software is going to be executed by a computer because he understood the underlying hardware. Today, people don't even see the servers, let alone know their inner details. All in all, this attitude toward ignoring things because they are simple or because they are auto-generated may lead to unwanted surprises and hard debugging sessions. This video is a story about why we need to question this attitude and why it's important to be knowledgeable about things happening under the hood. The table of contents is as follows. First, we will describe our use case to put things into a proper context. Then we will see why do we need memoization, at least why we think that we need memoization. Next, we will look at the differences between cold and warm caches. We will also see how Python supports memoization. We will reflect on the importance of monitoring the caching behavior. And finally, we will rethink our design choice to use caching. Here is the problem description. In order to avoid any unnecessary distractions, the basic problem was intentionally chosen to be as simple as possible, which is computing the nth Fibonacci number and outputting both its value as well as number of steps taken to calculate it. We will implement all this in Python 3.9. The essential part of our discussion will be, of course, on something different than the basic problem, and that's about demonstrating the dangers pertaining to uninformed usage of seemingly simple programming elements. Okay, so let's see why do we need memoization, which is a form of caching and associated with top-down dynamic programming. Here is the code, which is very simple and essentially following the recursive formula. Let me write down it for the sake of completeness. For n equals greater than 2, then we have a base case of f1 equals 1 and f0 equals 0. So these are the base cases. And the tuple is comprised of the first element is the value, and this one is the number of steps. And this one here is coming from the fact that in order for these guys to be called, this top function was also called before these. So this is the formula for the number of steps. And if you call this function with n equals 4, then the value will be 3 and the steps will be 9. And the reason is because the recursive tree is having 9 nodes, which are all recalculated by this brute force version. And these are the leaves. Okay, so let's see how this is executing or how this performs. So let me zoom in a little bit. First, let me test it with n equals 4. And yes, it's 3 and 9. And now let's see how it executes with 20. As you can see, about 22,000 calculations or steps were needed. And if we try to invoke this with 50, then it will run for a very long time. As a matter of fact, we cannot even wait it out, so I will interrupt it. So all in all, this basic version is definitely not satisfying our needs because it cannot even handle n equals 50. So we will need to apply memoization. Let's see how to implement memoization in Python and see the differences between cold and warm caches. Here you see two functions. One is ending with OK, and the other one is ending with bad. I will later explain why the second one is bad. Let's first focus on the first one. It accepts a store as an optional parameter. We see that the default value is set to none. And this is a mechanism for the client to control the caching strategy. The store is usually implemented as a Python dictionary. Now, if the client pre-allocates this dictionary and reuses it across function calls, then the client is implementing a warm caching strategy. And the term warm indicates that the cache is pre-allocated and filled with entries that may be utilized during the computation to speed it up. If the store is not provided, then at the top level function call, the store is going to be created here as an empty dictionary, and this is an example of a cold cache. Of course, this store is going to be reused deeper down in the recursive calls, but at the entrance it's going always to be empty, and that's why we are saying that we implement here cold caching. Now, the cache is used in a very straightforward manner. After testing the base cases, here we check whether we already have a result for this parameter n, and if yes, then we just return the result. Otherwise, we enter the calculation. Once we have the result, we first store it and then return it back to the client or to the previous function call. The only difference here is about the number of steps calculated, because here we don't have as many function calls as with the previous version without caching. And this number 2 is coming from this guy. This +1 is contributed by the parent function, and another +1 is coming from this feeb2. n-2 is absolutely guaranteed to be in the store, because once feeb1 returns, n-2 is already calculated. So let's see how this helps us speed things up. And because the code is now much faster, we will use timing or measure the time of execution. And I will use an opportunity here to introduce the timeit module. It's part of the standard library. It's a very easy way to perform timing of your function execution. So 100, and I will set the repetition counter to 10,000, and we have half a second. Now let's see what would happen if we will use warm caching. So I will pre-allocate the cache and pass it here. And as you can see, that's a really significant improvement. Okay, let's now return back to our source code and see the second version, which was marked as bad. What immediately pops up, and you might have noticed that this dictionary here is marked by PyCharm. And if you hover over, you will already see a warning from PyCharm that default argument value is mutable. Now, the problem is that if someone is unaware or doesn't understand why this warning is emitted by PyCharm, then people usually ignore warnings and they think, okay, that's just another warning. But unfortunately, this is not the case here. And especially if someone thinks that moving or reducing the number of lines of code would be a great idea by putting it here, then we may just say this is an extremely bad idea. Extremely bad idea. Because there is a huge difference between this version and this version. This dictionary here is going to be allocated and it will live somewhere in the system. But the problem is that you have absolutely no control over this guy. So you have no control over the store. And if this pattern or this way of doing things is spread out all over the code base, not to mention if this sort of a function is put in a shared library, then this is a path to a memory leak. Why? Because you have no control over this dictionary, which means it can grow uncontrollably. So there is no way to control the size of the dictionary. And except, of course, in the case that if a client all the time passes its own dictionary, this default version is very dangerous. And to demonstrate that this is really here a dictionary that's going to be reused across function calls and behaves drastically differently than this, okay, let me show you in a Python console that we will get the same timing results as with warm caching in the previous version. Let me zoom in again, import time it, and here we are. We got the same result as with warm caching before, which means that actually we do have here warm caching, but without any control. Let's see how Python supports memoization out of the box. Here is the version of the code that uses the cache decorator from the functools module. If you would like to memoize your function, that's enough to be decorated with cache. This cache has been introduced in Python 3.9. In previous versions, you would use something like this. This is, of course, still available in Python 3.9, but you also have this nice, simple wrapper around this same construct here. The max size parameter, by having it set to none, means that the size of the cache is unbounded. Now, the crucial question is, how is this different from the previous bad version that tried to achieve the same thing? Because the cache here is providing you warm caching by default. Well, the crucial difference is that here you have full control over the cache. You have full control over the cache. And this is very important. Now, okay, you have annotated your function with the cache. Is there anything else? Is there anything else that you should know? The answer is absolutely yes. And the reason is that if you are completely unaware of the underlying mechanisms related to the cache decorator, then you would end up in the same situation as with the previous bad version, because you would have an unbounded cache that you don't know how to manage. And this is now the moment to emphasize the following equality: inability to control things is equivalent to being uninformed about ability to control things. Because in either case, you will essentially drive the system into the same trouble. Now, we know that there are things that you should know, right? But what are those things? You need to know the decorator design pattern. You need to know the Python's decorator engine, mechanism, facility, whatever I will let me call engine. And also you need to know the specifics of this decorator. What does it do to this function? Because this is a business API, right? But there is something attached by this cache to this function, and that's a cache management API. And this is the cache management API that gives you full control. So let me demonstrate how this works. Run file in Python console. Let me zoom in a little bit. And here it is. So we have cache info, which gives us, you see, a statistics hits equals 0, misses equals 0, max size equals none, and current size is 0. So this is essentially the state of the cache at the beginning. So it's empty. Let's call our function, for example, with 100. Okay, so let's see now what do we get by cache info. We see that we have the number of steps required to calculate 100 is 199, and that's exactly the sum of the hits and misses, because we have 98 cache hits and 101 cache misses. And we have the current size is 101. Notice that it's 1 larger than 100 because we have the zeroth term as well. Let's call our function again with 100. And we can see that the difference is only that we have 1 additional hit, but no misses, and the current size is 101. And this asks us to answer a very interesting question, which obviously something is not right here. You see that the number of steps returned is misleading from our function. It is telling us how many steps would be needed using a cold cache, but we are using a warm cache here. So which means that this whole calculation of the number of steps was wrong. And this is something related to the requirements engineering that we are going to tackle soon, but we need to be aware of that the number of steps that our function returns is definitely not aligned with what we are getting by using warm caching. Let me try something more. Let me try to invoke our function with 500. Okay, that works. Let me invoke it with 800, with 1000. Okay, we have a maximum recursion depth error. Now, there are two things that you can do here. Immediately jump to increase the recursion depth limit by using the sys module and then set recursion limit, but there is something more interesting that you can do here. And we can borrow an idea from artificial intelligence algorithms called iterative deepening. And this is something that you can do with worm caching. And it's very simple, essentially. So we have, okay, let me print out the cache info. So we have first 500 elements of the Fibonacci sequence inside our cache. And we want to reach the 1000th. So what we can do is first try to attack a lower bound, for example 700, and then jump from 700 to 1000, and this works. And the reason why the previous call of 500 worked, because we first called our function with 100 and then with 500. So the 500, we managed to reach 500 because the cache already contained the first 100 items. So this is the way how you can creatively use worm caching, and this is another difference between worm and cold cache. There is one additional very important method here on the cache management API, and that's clear cache, cache clear. And if we clear the cache and invoke info, then you can see the cache is again empty. And this is the way how you can fully manage your cache. You can monitor your cache, and that's very important that you have an ability to monitor, to see the size, the current size. And if something is going wrong, then you can always clear the cache and regain the memory. In this final section, we will revisit the requirements and try to figure out the reason behind the issue with the number of steps. Requirements traceability is a type of control, and you cannot do proper software development without being able to map requirements to code and vice versa. Now assume that we have all these versions arranged in a chronological order, starting from the bare recursion, then manual memoization with cold or warm caching, auto memoization using Python's built-in feature, until we arrive at the moment when someone asks this profound question: do we need all this caching horror? And we must answer this question because this is a precondition for further evolution. The way how can we answer this question is by tracing back things into the past and understand history. And after we arrive to the bare recursion and again look at the requirement specification, then this red part is the problem. This red part is, first of all, suspicious. It's ambiguous. And it's most probably a pollution from solution space. Furthermore, look at this, think of the later. What if you think differently? Are you still okay with the requirement? As you can see, now that we understand the reason that this bare recursion appeared because of the bad requirement specification, and that someone in the past was unaware of the significance of proper requirements engineering practices, we are now free to switch over here to a more efficient bottom-up dynamic programming version, which can use a constant space. And of course, since this is happening here, we must be very careful to do this transition without breaking existing clients. This conclusion section enlists the key takeaways from this video. A simple construct may bear a complex behavior, which means that in order to use properly whatever is simple, you must understand everything behind it. Otherwise, you will be surprised in a way that we have demonstrated in this video. You are fully accountable and responsible for everything you deliver, be it explicitly or implicitly assumed. And by this I mean you are responsible for your own code as well as whatever you reuse. Without knowing what is going on in the background, you will not be able to ship dependable solutions. If you are unaware of things that are happening in the background, then you might risk of being surprised in production, and that doesn't end properly in most cases. Requirements engineering must be the epicenter of all your activities, and this is one of the reasons that TOGAF is putting requirements right into the center. Thank you very much for watching this video. I hope it was interesting and that you may use some parts of it in your daily practice. Thank you very much.